Good evening one and all. So in this video lecture I am going to discuss the construction of root locus with two examples. So these are the two examples we are considering. So the transfer functions are given. Okay. So the step 1. So in step 1 we are going to calculate poles and zeros and locate them on the S-plane. Okay. So in the first example, the characteristic equation is s into s square plus 4s plus 13 equal to 0. So the first pole becomes s is equal to 0. The remaining two poles can be calculated by solving s square plus 4s plus 13, and the values are minus 2 plus or minus j3. And we can see that these poles are plotted or located in S plane. Okay, the first pole at s is equal to 0, the second pole at s is equal to minus 2 plus j3, and third pole at minus 2 minus j3. Okay, the second two poles are complex conjugates. And coming to the second example, so in this case the characteristic equation is s into s plus 2 into s plus 4 equal to 0. Correspondingly, the poles becomes 0, minus 2 and minus 4. So these are located at correspondingly in this particular S plane. Okay, one at s is equal to 0 and another P2 at s is equal to minus 2 and P3 at s is equal to minus 4. Okay, next second step. See, in the first step what we have done is we have calculated poles and zeros and then we have located them on S plane, and in both the examples we considered there are no zeros. So if there is a zero, usually we will be using O notation. Okay, and for poles we are using X notation. Okay, next in the second step what we are trying to do is, see, we have S plane, right? We have S plane, and in S plane there is a real axis as well as imaginary axis. In the second step what we are doing is we are trying to identify if there are any root locus branch lying on the real axis. Okay, we have the real axis and we are just verifying whether there is any chance of getting the root locus branch on the real axis. Okay, we can verify that by checking one condition. The condition is, see, on the real axis you take one point, you take some point and let it be test point. You just verify if there are any odd number of poles and zeros towards right side. Okay, if that is the case, then that particular test point is on the root locus branch. Okay, so we have to go to the real axis and then we have to verify if there are any odd number of zeros and poles towards right side, okay, on the real axis. So if that condition is satisfied, then that particular point is on the root locus branch. So using this condition we are trying to check this particular step for these two examples. So in the first case, on the real axis there is only one pole P1 at s is equal to 0. Now obviously we can easily verify that if you take s is equal to minus 1 as the test point, there will be only one pole towards right side. Yes or no? But if you take at s is equal to 1, if you take the test point as s is equal to 1, then what will happen? Towards right side there are nothing, there are no pole or no zero. So that particular condition will not satisfy for s is equal to 1. But if you take s is equal to minus 1 or s is equal to minus 2, and for that matter if you take any negative values, then we will be getting only one pole towards right side. So the entire real axis for which values are negative, that is nothing but the root locus branch. Okay, because there is only one pole towards right side. So here we have shown that in red color, okay, that particular line, and it will reach to infinity, okay, starting from minus infinity to that particular s is equal to 0. So this is the this is the root locus branch. Okay, coming to the second example. In the second example, we don't have any poles or zeros towards the right side from s is equal to 0. Then you go to from s is equal to minus 2 to s is equal to 0. Okay, between that particular area, if you choose any test point, then obviously there will be one pole towards right side, which is s is equal to 0. So starting from s is equal to minus 2 to s is equal to 0, that particular range is satisfying that condition. So that is a part of root locus branch. And similarly, from s is equal to minus infinity to s is equal to minus 4, this particular range will also satisfy that condition. So in this case, we will be getting 3 poles towards right side. All 3 poles are towards the right side from s is equal to minus infinity to s is equal to 4. Okay, but if you take the area from s is equal to minus 4 to s is equal to minus 2, so towards right side there will be 2 poles, so which is even number of poles, but we should get only odd number of poles. If that condition is satisfied, then we can say that particular range is on the root locus branch. Okay, so from this discussion we can easily understand that the locations where it is highlighted in red color are the root locus branch. Next, the third step, here we are going to calculate angle of asymptotes and centroid. See, angle of asymptotes is the angle which the root locus branch will follow to reach to infinity or to come from infinity. See, why you are thinking about infinity means, if there are, we already know that the root locus branch start from poles and end at zeros. For instance, if we have equal number of zeros and poles, for example, we have 3 poles and 3 zeros, then there will be 3 root locus branches. The first branch will start from first pole and end at first 0. Similarly, the second and third. But if, for instance, if we have 3 poles and only 1 0, we have 3 poles and only 1 0, then the first branch may start from 1 pole and end at the 0. But the remaining 2 branches need to start from, they will be anyway starting from the poles which we already have, but where will they end? They will end at infinity. So these branches should go towards infinity, right? So in that particular case, the angle which they follow is the angle of asymptotes, and this is the case where we have more number of zeros. In that case, the root locus branch will start from infinity and end at a finite 0. Okay, in that case also the angle of asymptotes is required. So how we calculate that? Means plus or minus 180 into 2 cube plus 1 divided by n minus m. N is number of poles, m is number of zeros. Okay, so we will apply this particular formula to the examples we have. And before that, we have centroid. So what is centroid? The meeting point of asymptote with real axis. Okay, see, asymptotes, actually the root locus branch will change its direction at this asymptote. We will see how in these 2 examples. And the formula to calculate centroid is sum of poles minus sum of zeros divided by n minus m. So in the case of first example, we know P1 is equal to 0, P2 equal to minus 2 plus J3 plus, and P3 is minus 2 minus 3J, and angle of asymptotes, as we discussed, it is plus or minus 180 2q plus 1 by n minus m. So here n is 3, m is 0. and the range of q is from 0 to n minus m. So n minus m here is 3. So 0, 1, 2, 3. So we are going to substitute q is equal to 0. That time the angle is plus or minus 60. q1 is plus or minus 180. q2, q3. So we will be calculating the angles. Okay, see here when we cross 360, then automatically it becomes a 0. Okay, 360 degrees is nothing but a 0. Similarly, if it is 60 short of 360, that is 300 is 60 short of 300, so we can take it as minus 60 also. Okay, and coming to the centroid, the sum of poles. So we are calculating sum of poles. Anyway, zeros are not present in this example, and divided by n minus m, which is 3. So centroid is minus 4 by 3, which is minus 1.33. So we will see how we are using these angles as well as centroid in plotting root locus. And before that, in the second example, we know the poles, and here also there are 3 poles, and we will be getting 4 angles as well as the centroid. So sum of poles minus, here also zeros are not there, so divided by 3. So here we will be getting minus 2. Okay, now so how we are using these angles. So let's see. Now what is the centroid? For the first example, minus 1.33. First of all, you locate in the S plane. So we have located here, and then angle of asymptotes. So what is the angle of asymptotes? 60, then 180, then minus 360, and again 60. So here the first angle, so starting from this particular point, so 60 means, so this is the original axis, so 60 degrees, this is the first one, and 180 is this one, second one, and then minus 60, so this is the one, and again 60 will come. So actually here if you observe, 1, 2, 3, fourth one is the first one only, so it is repeating. So we have only 3 angles here. The first one is this one, 60 degrees, second one is 180, this one, third one is minus 60, this one. Okay, you just plot them. After plotting, so we will be having the directions of asymptotes. Okay, similarly in this case also, the centroid is at minus 2, and first one is 60, second one is minus 180, third one is, sorry, second one is 180, third one is minus 60. Next, breakaway and break-in points. See, breakaway and break-in points. See, let's take the real axis. Okay, on the real axis, let us assume that there are 2 poles. We have 2 poles. Okay, adjacently, there are 2 adjacent poles on the real axis. Then the branch will start from them and end at 0. They have to go further. So there is a possibility, there is a chance that the root locus branch from one pole is towards another branch which is starting from another pole. That time they both will meet at one point and they will go out of that particular real axis. Okay, so that particular point where the root locus branch is coming out of the real axis, we call it as breakaway point. Similarly, when there are two zeros and there will be 2 branches coming either from poles or infinity and reaching at these zeros, if they are coming, if the direction of these branches are exactly reverse, then they will join. Okay, they will break in to this particular real axis. That time we need break-in point. So how we calculate this? Means we are going to take the characteristic equation and we are going to calculate k. Okay, and then we are going to take dk by ds. We are going to differentiate this k with respect to s and make it equal to 0. Okay, and then we have to calculate the value of s for which k is positive and real. Okay, we have to calculate. Say after writing the right expression for k, we are going to differentiate it with respect to s and make it equal to 0. Then we are going to calculate the value of s for which k is real and positive. So let's see in the example. So in the first case, so c of s by r of s is, so actually the g of s is open loop transfer function, and when we take the closed loop transfer function, it will be j of s by 1 plus g of s. So we can minimize it. And what is the characteristic equation there? S into s square plus 4s plus 1.3, sorry 13 plus k equal to 0. Okay, then what is k? We have written the expression for k as minus s cube minus 4s square minus 13s. Then differentiate it and make it equal to 0. Okay, and then calculate s. We got two values for s. Then we have the expression for k. So what is the expression for k? S minus s cube minus 4s minus 13s. Now you substitute these two values. Okay, so when we substitute minus 1.33 plus j 1.6, we are getting s as this particular value. Okay, similarly if you substitute, actually in this particular case when you substitute this kind of value, we are getting complex value, but our condition says that we have to find out the value of s for which k is real and positive. Okay, but this is not real value, it includes imaginary values also, so we cannot take this particular s. Similarly if you substitute another s value which is minus 1.33 minus 1.6, in that case also you are going to get a complex number. Okay, so because of that, this particular root locus has neither breakaway nor break-in point. Okay, so this is obvious. The reason is, so in the first example there is only one pole. Okay, in that case, in most of these kind of cases there is no need of breakaway or break-in point, but in this case because there are two poles, there will be one break-in, breakaway point. So let's calculate that. So first of all we are calculating the gain, and then we are minimizing it, and we are taking the characteristic equation, and we are writing the expression for k and differentiating with respect to s and make it equal to 0. Calculate s. We got two s values and we are substituting these s values in this k. So we got k is equal to 3.08 and k is equal to minus 3.08 for these two s values, but our condition says that we have to get positive and real. So out of these two, positive is only one value, that is 3.08. so what is the value of s at that particular point? S is equal to minus 0.845. so this is breakaway point. So we are just locating that particular point here. Okay, so this is step 4. Next, coming to step 5, angle of departure and angle of arrival. So angle of departure and angle of arrival, so basically we are using these angles when there are complex poles. Okay, when there are complex conjugate pole, anyway we will be discussing that in with the examples we have. The relation or the expression to calculate angle of departure is 180 minus sum of angles of vector to the complex pole A from other poles plus sum of angles of vectors to the complex pole A from zeros. Similarly, we have another expression for angle of arrival. Let's see how we calculate. See, this is the S plane, and this is the negative side of S plane. Here let's take this as a pole. We have this pole and you observe this is a pole, this is a 0, and this is a 0, and this is a pole. We have 4 okay, actually this I have taken only part of the figure. We have one more pole here, which is A complex conjugate. So let's okay, here we have one more pole. Okay, now we have 1, 2, 3 and 4 poles and zeros. How many? 1, 2. 2 zeros are there. Now what is the formula? 180 minus sum of angles of vector to the complex pole from other poles. Okay, now with respect to this particular pole, we are calculating the angles. Okay, so before that we have to draw the vectors from this pole, from this pole, and from here there is one more pole which is A complex conjugate. So we have drawn these vectors, as well as from zeros also, from here and here. Okay, we have 5 vectors associated, and then actually we want angles of vectors, right? Angles of vector. So this is theta 5, this is theta 4, and this is theta 3, and this is theta 2, and this is theta 1. So how we calculate these angles, that is secondary. So because that is easy, because if we have the length of this base as well as this height, by using trigonometric relations we can get the angles. Okay, so from this formula, what is the angle of departure? Angle of departure is 180 minus angles associated with poles. Okay, so theta 1, and this is theta 3, and this is theta 5 we have written here, and plus angles associated with zeros. So there are 2 zeros. So theta 2, theta 4. So this is theta 2 and this is theta 4. Okay, so this is angle of departure. Similarly, angle of arrival. Okay, and in our examples, so this is our first example. So here these are the 2 poles. Okay, these are the 2 poles. Now let's consider pole 2. Let's consider this particular pole. Now, and how many other poles are there? Here this is one pole as well as this is another pole. Now the angle associated with this particular vector, I have not plotted the vector. So from P1 to P2 there is a vector. Okay, let's assume that there is a vector. Now what is the angle associated with this? So actually from here to here this is 180, and from 180 we have to subtract this particular angle. We have to subtract this particular angle. So for that the formula is tan inverse. So this length is 3 and this length is 2. Okay, this is 3 and this is 2. So tan inverse 3 by 2. So the value is 123.7. The other pole is this one. This is the vector associated, and angle is exactly 90. Okay, now if you add the, okay, now you substitute in this formula. Okay, anyway we don't have any zeros, so we have to subtract the sum of those two angles from 180. So we will be getting minus 33.7 degrees, minus 33.7 degrees, and angle of departure at pole 3. So we have calculated with respect to pole 2 now. Similarly, we can calculate the angles with respect to pole 3. So that time we will be getting plus or minus 33.7. Okay, these are the angle of departure at different poles. And coming to the second example, so in this example there are no complex pole or zero. There are no complex poles or there are no complex zeros. So that's why we need not calculate angle of departure. So now, so using this angle of departure at these two different poles, what we are doing is we are just plotting a line. Okay, so here for the first case the angle is minus 33.7. so actually 33.7 means it will be somewhere here. So minus 33, so the same downwards. So we are plotting a line, and here plus 33. So this is plus 33 with respect to this particular pole 3. How we are using this, we will see in the next steps. Okay, next one, next step is point of intersection of root locus with imaginary axis. See, the root locus branch may cross the imaginary axis. See, this is very crucial because for instance, if the root locus branch is starting or is lying on the left side of the imaginary axis, the system is stable. Now, as and when the root locus branch starting to move towards imaginary axis and towards crossing the imaginary axis, that time what is happening, the system is becoming unstable. Okay, so we have to identify the point of intersection between the root locus branch and the imaginary axis, as well as at that particular point what is the gain of the system. Okay, so if we are trying to increase the gain, if that particular case may arise where the root locus branch will go out of the left side, that time the system becomes unstable. Okay, so how we calculate the third step, we are going to use this third step. So anyway, directly we will see in the example. See, what we are doing is how we are calculating that point we will explain here. So this is the transfer function and this is the characteristic equation. Now just to substitute S is equal to j omega in this equation. So substitute S is equal to j omega, minimize it. Okay, and here in this expression we will be getting real as well as imaginary. Okay, take the real part, make it equal to 0. Okay, take the real part and make it equal to 0. Calculate that omega, and this value, so this value gives the intersecting point of the root locus branch with the imaginary axis. Okay, so this is a plus 3.6 and minus 3.6, and now if you take the imaginary part, okay, previously we have taken imaginary part, sorry, so we have taken imaginary part, now you take real part. Okay, you take real part and use this value to calculate k. So k is equal to 52. See, k is equal to 52. So at that particular point where the system is becoming unstable, is k is equal to 52. Okay, not becoming unstable, that is critically stable, because currently the root locus is just touching the imaginary axis. It is not going towards it is of course going towards right side, but it has not done so far. So k is equal to 52 is the maximum gain where the system is stable. Similarly, for the second example, we have written the characteristic equation, then substitute S is equal to j omega, then take imaginary part of the above equation and make it equal to 0, calculate omega, so which will give us the point, that is intersection point between the root locus branch and the imaginary axis, and then take the real part and make it equal to 0, then calculate gain. Okay, so 48 is a maximum gain for the second system. Now see, we know that the root locus branch started pole. Okay, so here a pole is the root locus, here one pole is there, here one pole is there. We have already by using in the previous step, here by using angle of departure. Okay, angle of departure, we have already drawn one line. Okay, we have already drawn this line. Now root locus branch will start here. Okay, and it will not cross this line, it will start to fall down, and we have centroid, right? We have centroid. At that particular centroid, the root locus changes the direction, and it will go towards infinity, and the crossing, the intersecting point we have calculated to be 3.6. okay, so here it is crossing and it is going parallel to the asymptote. This is the asymptote. okay, this is the asymptote. So it will go, as it is going towards infinity, this line as well as the asymptote line will be in parallel. okay, so here also the same thing is happening. So this is centroid. At centroid the direction changes, understand? So this is with respect to first example. And in the second example we have, see, this is the first branch. So it is completely one branch. The other branch, see here, at this point it is starting, one branch is starting from here and another branch is starting from here, and we have calculated breakaway point, right? We have calculated we have calculated breakaway point here. okay, in the previous in step 4, in the step 4 we have calculated breakaway point. okay, so one branch, one root locus branch will start from here and travel like this, and another branch start from here and travel to this point, and then this will be splitted. One branch will go this direction, another branch will go this direction, but they will be going parallel to this asymptote, and the intersection point is, I think, 3.8, some value we calculated just now. So let's see those values now. It is 2.8. okay, so at this point it is starting and it is going like this, similarly in this direction also. So these are the root locus branches. So this is the first example. This is one, so starting from here and going towards infinity, and this is the second one, and this is the third one. Similarly here, this is the first one, and this is the second one, and this is the third one. okay, thank you.